Space travel, it sparks the imagination. We look up and wonder about the stars. Could we travel to them? The answer is yes, we already have. Humans have walked on the moon. We've sent probes to distant planets, and we're just getting started. But how does space travel work? It starts with Newton's third law of motion. For every action, there's an equal and opposite reaction. This is the foundation of rocket propulsion. To escape Earth's gravity, we need escape velocity. Imagine throwing a ball upwards. It goes up, slows down, then falls back. Now imagine throwing it with enough force to overcome gravity. That's escape velocity. Space travel is complex, but understanding the basics helps us grasp space exploration. In the following sections, we'll delve deeper into space travel. Newton's third law of motion is fundamental to space travel. For every action, there is an equal and opposite reaction. Imagine a balloon filled with air. Let go, and the air rushes out. The reaction is the balloon shooting forward. Rockets work similarly. Expelling gas downwards propels the rocket upwards. This thrust allows rockets to overcome gravity and soar into space. Rockets are incredible feats of engineering. They are specifically designed to overcome Earth's gravitational pull. This is no easy task. It requires immense power, careful design, and a bit of rocket science. At the heart of a rocket is its engine. The engine's job is to burn fuel and produce thrust. The fuel is mixed with an oxidizer, which allows it to burn even in the vacuum of space. The burning fuel creates hot gas that expands rapidly. This hot gas is then channeled through a nozzle. The nozzle is shaped like a bell and is designed to accelerate the gas to extremely high speeds. As the gas exits the nozzle at high speed, it creates thrust. This thrust propels the rocket upwards, counteracting the force of gravity. It's all about momentum. The faster and more massive the expelled gas, the greater the rocket's momentum in the opposite direction. This is how rockets achieve the incredible speeds needed to escape Earth's gravitational grasp. Launching a rocket into space is a complex process. It involves multiple stages, each with a specific function. These stages are jettisoned as they are depleted, making the rocket lighter and more efficient as it climbs higher. The first stage is the most powerful. It's responsible for lifting the entire rocket off the launch pad and overcoming the initial gravitational pull. This stage typically has the largest engines and carries the most fuel. Once the first stage has burned all its fuel, it separates from the rest of the rocket and falls back to Earth. The second stage then ignites, continuing to propel the rocket upwards. The second stage is smaller and lighter than the first stage, as it doesn't need to carry as much weight. Some rockets have a third stage, which is even smaller and lighter. This stage is responsible for achieving the final velocity needed to reach orbit or escape Earth's gravity altogether. Each stage plays a crucial role in the rocket's journey to space. Section 5. Orbiting Earth. A delicate dance of speed and gravity. Imagine throwing a ball horizontally. It travels forward but also curves downwards due to gravity, eventually hitting the ground. Now imagine throwing it with enough force that its curved path matches the Earth's curvature. That's the basic idea behind orbiting. An object in orbit is essentially in a constant state of freefall. It's constantly being pulled towards Earth by gravity. However, its forward velocity is so great that it keeps missing the Earth as it falls. This delicate balance between gravity and forward velocity is what keeps satellites and spacecraft in orbit. The speed required to maintain orbit depends on the altitude. Lower orbits require higher speeds, while higher orbits require lower speeds. Orbiting is a fundamental concept in space travel. It allows us to keep satellites in space for communication, navigation, and Earth observation. It also serves as a stepping stone for missions to other planets and beyond. Section 6. LEO versus GEO. Different orbits, different purposes. Not all orbits are created equal. Different orbits serve different purposes. Two of the most common types of orbits are low Earth orbit, LEO, and geostationary orbit, GEO. LEO is a region of space a few hundred miles above Earth's surface. Satellites in LEO travel at high speeds, completing an orbit every 90 minutes or so. This makes LEO ideal for Earth observation satellites, as they can cover a large area of the planet in a short amount of time. GEO is much higher than LEO, at an altitude of about 22,000 miles. Satellites in GEO orbit at the same speed as Earth's rotation. This means they appear to hover over the same spot on Earth. GEO is ideal for communication satellites, as they can provide continuous coverage to a specific region. Choosing the right orbit is crucial for a mission's success. It depends on factors such as the satellite's purpose, its instruments, and its communication requirements. Section 7. Life support in space: breathing, drinking, and staying warm. Space is a harsh and unforgiving environment. There's no air to breathe, no water to drink, and extreme temperatures. To survive in space, astronauts need sophisticated life support systems. One of the most important systems is the Environmental Control and Life Support System, ECLSS. This system is responsible for providing a breathable atmosphere, regulating temperature, and managing waste. The ECLSS uses a variety of technologies to achieve these tasks. For example, it uses filters to remove carbon dioxide from the air and adds oxygen to maintain a breathable atmosphere. It also uses heaters and coolers to regulate temperature, ensuring the spacecraft remains comfortable for the crew. Water is another crucial resource in space. The ECLSS collects and recycles wastewater, including urine and sweat, to provide drinking water for the crew. Life support systems are essential for human survival in space, enabling us to explore this hostile environment. Section 8. Apollo to SpaceX, milestones in space exploration. Since the dawn of the space age, we've witnessed incredible milestones in space exploration. From the first human steps on the moon to the ongoing quest to Mars, each mission has pushed the boundaries of human ingenuity. The Apollo missions, which landed the first humans on the moon in 1969, remain a defining moment in space exploration. These missions captivated the world and demonstrated the immense capabilities of human ambition and technological prowess. In recent years, private companies like SpaceX have emerged as major players in space exploration. SpaceX's Falcon 9 rocket and Dragon spacecraft have revolutionized space travel by making it more affordable and accessible. From robotic rovers exploring Mars to telescopes peering into the depths of the universe, space exploration continues to unveil the mysteries of the cosmos and inspire future generations. Section 9. The economics of space. Is it worth the investment? Space exploration is an expensive endeavor. It requires significant financial investments in research, development, and infrastructure. This raises the question, is space exploration worth the cost? Proponents argue that the scientific discoveries, technological advancements, and economic opportunities generated by space exploration far outweigh the costs. For example, technologies developed for space travel often find their way into our everyday lives, from GPS navigation to scratch-resistant lenses. Furthermore, space exploration inspires innovation and pushes the boundaries of human knowledge. It encourages us to think big, solve complex problems, and strive for something greater than ourselves. However, critics argue that the money spent on space exploration could be better used to address pressing issues here on Earth, such as poverty, hunger, and climate change. The debate over the economics of space exploration is complex and multifaceted. Section 10. Humans versus robots, the great space exploration debate. As we venture further into space, a fundamental question arises: should we send humans or robots? Both approaches have their advantages and disadvantages. Human exploration offers unique capabilities. Humans possess adaptability, creativity, and problem-solving skills that robots currently lack. Astronauts can make real-time decisions, adapt to unexpected situations, and perform complex scientific experiments. On the other hand, robotic missions are significantly cheaper and less risky. Robots can withstand the harsh conditions of space, operate for extended periods without needing life support systems, and explore hazardous environments that would be too dangerous for humans. The choice between humans and robots often depends on the specific mission objectives. For tasks requiring human intuition and dexterity, human exploration may be preferable. For missions focused on data collection and exploration of hazardous environments, robots may be the more practical choice. Section 11. Space colonization and tourism, dreams of the future. As we continue to explore space, the concepts of space colonization and space tourism are moving from the realm of science fiction to the realm of possibility. These endeavors offer both exciting opportunities and significant challenges. Space colonization, the establishment of permanent human settlements beyond Earth, presents a potential solution to overpopulation, resource depletion, and other challenges facing our planet. However, it also poses significant logistical, ethical, and technological hurdles. Space tourism, on the other hand, offers the allure of experiencing the awe-inspiring beauty of space firsthand. While still in its infancy, space tourism is rapidly gaining popularity, with companies like Virgin Galactic and Blue Origin offering suborbital flights. The future of space exploration holds immense promise. From unlocking the secrets of the universe to expanding our presence beyond Earth, the possibilities are limitless.